Hi, stats students. Welcome to section 10.1b. We're finishing off our section about our correlation coefficients, our scatter plots, calculating R. And in this section, we're going to test the significance of R. So we're actually going to do a hypothesis test. There's a little bit of difference from our previous ones. It's probably a little shorter, but we have to have found R in order to do this. So if R is not equal to 0, remember, if R equals 0, there is no significant relationship between our variables. So if R is not equal to 0, there's two possibilities. The value of R is high enough to conclude that there is a linear relationship between the two variables, or it's due to chance. Again, we're looking to see if there is a relationship, right? That's kind of our goal. So we've got some assumptions to make here. First of all, the data have to be quantitative, so numerical. We've got ourselves a simple random sample. The scatter plot that we made way back shows that there is some sort of linear relationship. Again, if we didn't see a relationship, we calculate R, it's close to 0, we don't have anywhere else to go. There are no outliers. Remember, in the last section we said R is particularly susceptible to outliers, so we do need to make sure we've got no outliers in our data, and the variables X and Y come from normal distributions. So we keep going back to those normal distributions. So when we do a hypothesis test, first of all, we keep using our Greek letters in our H sub O and our H sub 1 because that's what we're looking at, and then we're using sample data to test it. So our H sub O every time is going to be rho equals 0. Remember, rho is the correlation coefficient for the population. R is the correlation coefficient for the sample. H sub 1 is always going to be rho is not equal to 0. We will probably, we will be doing two-tailed tests like this. We could do a one-tail, but we'll stick to the two-tailed. So if rho is not equal to 0 in H sub 1, that means there is a significant linear correlation. If rho is equal to 0, remember, there is no correlation. So we're seeing which one we like. Are we going to reject H sub O? If we reject H sub O, that means we think there is a linear correlation. If we do not reject H sub O, that means there is none. So there's three methods to test the significance of our correlation coefficient. The first one is our traditional method. We would use the t-test in the t-table. I'm going to tell you what that looks like, but I don't think this is the easiest method. We could do the p-value method. Again, we would go to the t-table, and this would be inexact. This would be one of those things that the p-value is somewhere in between this and this. So not super great for this situation. And then the one that we like the best is to find the critical value of R using yet one more table, Table I, in the back of the book. This is on page 788. It's actually the left side of the page. So we'll do that one. So we'll talk very briefly about the first two. Actually, we probably don't even really need to talk about the first two, right? So if we're doing our traditional method, remember, we're going to find our critical value, and we're going to do our test value. And then all the rest stays the same. I don't even know if you want to write this down. Do our hypotheses, make a decision, summarize, blah, blah, blah. So we know all that. We've done that. The test value is always what changes up, as well as where we find our critical value. The critical value will come from the t-table. And the test value looks like this. T equals R times the square root of n minus 2 over 1 minus R squared. Notice we need to have already calculated R, the correlation coefficient. This way works, this is good, but it feels like more work than the other way. So this is for the traditional method. I am going to suggest that we don't use this. I do need to point out a couple things over here in the side box. This is the first time we're going to change up degrees of freedom. DF, we need to go with n minus 2. That's how many values are free to vary. So we have less wiggle room for this one. So n minus 2 is what we're going to use for our degree of freedom for for chapter 10, let's say. And n is the number of ordered pairs we've got. So our number of x's and number of y's will match. All right, so, I mean, that's cool and everything, but p-value method, I'm not even going to tap these in. We weren't using this a whole bunch, and this is very inexact. Again, we'd use that table I. This is the one that we want to talk about. Whoop. Oh, there we go. So step 1, a lot of this is really the same. So we are doing the R method because we're going to use our R, our correlation coefficient of hypothesis testing for the significance of R, and we're going to use this for two-tailed tests. We could go to one-tailed, but that would be like the next step. So let's figure it out two-tailed. We know step 1, state our hypotheses, right? And I told you what that was going to be. Rho equals 0 and rho is not equal to 0. Step 2, find the critical values of R from table 1. Again, that would be on page 783. Nope, 788. Next, compute the correlation coefficient. This is from section 10.1a. So hopefully you figured out how to do all that calculator work and the sum of your x times y's and the sum of your x's and all those other things. So this is what we're going to use as our test value. So I put no test value needed. This is what we're going to compare to our critical value. So we just have to calculate R. So we don't even have to do another formula like that T equals formula that I just showed you for the traditional method. So this is going to be our preferred method. Unless you want to do it the other way, then I can definitely help you out with that. But the test value is going to be the value of R, basically. Step 4, we know, make a decision. Your two choices, reject H sub O or do not reject H sub O. Step 5 is summarize. Here are your choices for summarize. We're not even going back to that table. You are either going to say there is a significant relationship, that's if we reject H sub O, or there is not a significant relationship between whatever the situation is. Is not is if we do not reject, because that means we think that rho is equal to 0, which means there's not a significant relationship. All right, so let's do an example and I'll be done talking. So example 10.5c, test the significance of the correlation coefficient in example 10.4. This was back in section 10.1a, and it was about teachers and the number of pupils per teacher, and we hopefully have calculated that correlation coefficient. So I'm going to speed through that part because that's something that we hopefully calculated already. So step 1, we've just got to state our hypotheses. So it says for the number of teachers and number of pupils per teacher data in section 10.1a, test the significance of the correlation coefficient, use alpha equals 0.05. You're going to see when we look at table I, the alpha values are relatively limited. There's only a couple. 0.05 is going to pop up a lot. So step 1 is always hypotheses, right? We're not even asking the claim because all we're looking at is rho equal to 0 or not equal to 0? So H sub O is always the equality hypothesis. H sub 1 is the inequality, and again, we'll always use two-tailed. There are one-tailed tests out there. Step 2 is to go to find our critical value. So we are going to go to table I on page 788. Couldn't hurt to take a break and take a look at this. I believe that our n was equal to 10. We had 10 pairs of data in that number of pupils example. So if n equals 10, remember degree of freedom for this chapter is n minus 2. So we've got to use a degree of freedom of 8. Watch that. That could be because we're so accustomed to doing what we do. We know that our alpha is equal to 0.05. So that means that our critical value from table I, when I look back, I'm going to look at the alpha equals 0.05. It's on the left side of the page. Go down to degree of freedom of 8. And I ended up with a critical value of 0.632. Now, this is two-tailed, positive and negative. Let me show you what we're looking at for you visual people. Here's 0. Remember, correlation coefficient goes from -1 to +1 inclusive. So what I'm saying is that at 0.632, so about just over halfway in the positive, and negative 0.632, those are our shaded regions. So that's what we're looking for. The shaded regions, remember, are always on the outside edges. So we got to go back to section 10.1a or a warm-up or wherever we found it. We probably, hopefully, calculated that our correlation coefficient was at 0.442. This is a lot more work than just writing down 0.442. We need to go back to section 10.1a and do the calculation for R. So I'm skipping over that like that's a super easy step. So step 4, we need to make a decision. So 0.442 on this number line from -1 to +1 would fall about right here, right? So that's definitely in the non-shaded, non-rejection. Do not reject H sub O. Which means we like that that rho is equal to 0. So if rho is equal to 0, we are going to say that there is not a significant relationship, is not, because rho equals 0 and 0 is no relationship. There is not a significant relationship between, remember I always want the context, the number of teachers and the students per teacher. And students per teacher. Hypothesis test done. So really there isn't a significant difference here. That is what we're doing in section 10.1b, so we needed to get all the calculations done before we could actually use that R value in a hypothesis test. There's another example. I'm going to skip it. We could probably do that. Just went back to another example. So I'm trying to find the examples that we've already calculated R, because that saves us a little time. Think about calculating R within the problem itself. It could take some time. So we need to just make sure we've got R down first. That is it for section, oh wait, there's one more thing that I want to say. So correlation and causation. So when we have rejected H sub O, and for whatever alpha value we pick, so we've rejected H sub O, that means rho is not equal to 0, that means there is a significant relationship between them. Any of the following possibilities can exist. There's a direct cause and effect relationship. Could happen. There's a reverse cause and effect relationship, inverse type of situation. As one increases, the other decreases, so a negative correlation. The relationship could be caused by a third variable that we hadn't thought about or tested for. So remember, we think there's a relationship, but there's all kinds of things happening. Way back at the beginning, we called them confounding variables. They're things that could also affect our outcomes. There could be a complexity of interrelationships. So more than just a third variable, there could be a third, fourth, fifth, and 10th variable that is affecting our data. And it could just be a coincidence. Who knows, right? We think, we're pretty sure at a 95% confidence level that there is a relationship or a correlation. But remember, this is that 5% or whatever else we might be. So this is that beta, that the possibility that it could be just a coincidence. Here's the caution. I want to make sure that I mention this. This is the important part. Correlation between two variables does not necessarily imply causation, so it might not be a cause and effect. If you do this, then that happens. It might not be that. So we don't want to just say, oh, we said that there's a relationship, that means that this causes this. There's a lot of other things that could be in play here, including other variables, coincidence, whatever it might be. So we just say a correlation, it's technical statistical talk. We cannot necessarily say it's causation. More study would need to be done. Now I am done with section 10.1b. Thanks for hanging in there. Have a fabulous day. I'll see you next time.